This is problem number 12 on page 78, chapter 4. The problem's about gives us information about a proton that its velocity at time 0 is 4I minus 2J plus 3K. And then 4 seconds later, its velocity is negative 2I minus 2J plus 5K. First question is, what is the proton's average acceleration in unit vector notation? And then the second part is, what is the magnitude of that average acceleration? So, by definition, the average acceleration is change of velocity over change of time. So we would look at the velocity at time 4 minus the velocity at time 0. And if we subtract the I components, negative 2 minus 4, we would get negative 6I. If we subtract the j components, negative 2 minus a negative 2 would be 0j. And then the k components, 5 minus 3 would be 2k. And then change of time would be 4 seconds. Dividing each one of those components by 4, negative 6 divided by 4, 1.5, or negative 1.5i. 0 divided by 4, of course, is 0, and then 2 divided by 4, 1/2 k. So there's the answer to the first question in unit vector notation for the average acceleration. And then the magnitude, again, of any vector, is we will square each component of the vector, add those sums together, and then square root. So this one comes out to be about 1.6 meter per second squared, since we would have the velocity would be in meters per second, the time in seconds, and when we would divide, then we would get meters per second squared. Okay, at the bottom of the screen, the next question is, what is the average acceleration vector? What angle does that vector make with the positive x-axis? So if we put, since we're only in 2 dimensions, the vector only has an I component, which is in the x direction, and a k component, which is in the z direction. If we think of that vector, negative 1.5i would be in the negative x direction 1.5 units, and positive 1/2 k would be in the positive direction. So there's our vector in red. To answer the question, what angle does the vector make with the positive x-axis, we want the blue angle phi at the bottom of the screen, but we're going to actually go into the right triangle on the left, the red right triangle, and find theta. Since we know the side opposite and adjacent, we can solve for theta and get inverse tangent of 0.5 divided by 1.5. That angle is approximately 18.4 degrees, and so phi, the angle that we want, would be 180 minus that, giving us 161.6. Now in this example, since we were in 2 dimensions, the vector only had an I and k component, we were able to find the angle with respect to the positive x-axis. But if we would have had all 3 dimensions, then this technique wouldn't really work very well. So on the next screen, I'm going to go back and have the same average acceleration. Okay, and then if we thought of a vector that's going in the direction of the positive x-axis, we could really say anything times I. So I'm going to define vector B as 1I. And so the smallest angle between the average acceleration vector and vector B, we can use our formula that we developed for dot products. In other words, between any 2 vectors, if we call them A and B, the dot product equals the length of the 2 vectors multiplied together times the cosine of the angle between them. So in our example, what is the dot product of our average acceleration vector and vector B? Well, when we multiply the x components, negative 1.5 times 1, we would get negative 1.5. And since the average acceleration vector doesn't have a j component, vector B doesn't have a j component, we'd really get 0 times 0 is 0, and then the average acceleration vector's k component, 0.5, times the vector B's k component, 0, would be another 0. So The dot product in this case will just be negative 1.5. And then on the right-hand side of the equation, for us to find the links of vectors A and B, vector A, again, we've done previously. We would square root the sum of each component squared. And then looking at vector B, 1i, it's just 1 unit long, so B would be 1 unit times the cosine of the angle between it. So now if we divide both sides by the radical, the square root, and take the inverse cosine, we would have the inverse cosine of negative 1.5 over the square root of 2.5, and then in degree mode, entering that into a calculator, we get the same answer as a while ago, 161.6 degrees. Again, this method would work for, if we had a vector in 3 dimensions, we could still find the angle between that and the positive x-axis by letting a second vector b equal 1